In this video, we'll begin discussing redox reactions and the idea of an oxidation number. Redox reactions, or the so-called oxidation reduction reactions, involve the transfer of electrons from one of the reactants to another and involve changes in the hypothetical oxidation numbers of atoms involved. The overall reaction that you see here, in which you take iron, in this case an iron nail, and place it in contact with copper 2 sulfate solution, the deep blue solution that you see, results in the transfer of electrons from the iron to the copper 2 ions that are in solution, and ends up depositing copper metal on the surface of the nail. And so in this case, you can see that after the nail is taken out, you see the brown copper coating that is on the surface of that nail. In a way of representing this reaction, we can write the formulas for both the reactants and the products of the overall reaction in the form of the molecular reaction. But indeed, we can also represent this reaction in terms of a complete ionic reaction by dissociating the ionic species of copper sulfate and the iron 2 sulfate, so that we have the ions that are actually present in the solution. You'll notice that in this particular case, then the sulfate represents a spectator species and can be canceled out, so that when we write the overall redox reaction for the net ionic reaction, we have a situation where the electrons are being transferred from the iron, which is elemental iron having a 0 oxidation number, going to the copper 2 plus, and converting the iron into the product of iron 2 plus and the other product being copper metal. At this point, we need to discuss the concept of an oxidation number. This is simply a bookkeeping way of keeping track of the electrons that are involved in the transfer from one species to another, and there are a set of rules that we'll have to understand. Shown here are some of the rules for assigning oxidation numbers to various species. The first rule is any element is assigned an oxidation number of 0 because there are the same number of protons in the nucleus as there are electrons orbiting the nucleus, so no net charge. In the second case, if I have a monoatomic ion, either a cation or an anion, the oxidation number corresponds to the charge of that ion. 3, typically oxygen forms an anion, and the anion is 99% of the time -2. There is one exception for oxygen, that is the so-called peroxide ion, where it could be -1. The fourth example here is for hydrogen. Typically, we count the oxidation number of hydrogen as +1. There are some exceptions to this, especially if there is a metal ion as the first thing in the formula, and then hydrogen ends up being the second thing in the formula, and in that case, the hydrogen is acting as an anion, or a so-called hydride. The halogens almost always form -1 ions, so the oxidation number is -1. And then finally, for polyatomic ions, we have to determine the oxidation number as a result of determining what the net charge of that ion is, and using the other rules having to do with the oxidation numbers for the other elements involved. as an example of how to go about determining the oxidation number of an atom in a particular compound, this is have to remember that this is simply a hypothetical assigning of a charge to an atom. It doesn't necessarily represent the real situation, especially if we're dealing with molecular compounds where we have covalent bonding. So, as an example, in the molecule carbon dioxide, we'd like to know what the oxidation number is for the carbon. Well, it turns out oxygen is more electronegative than carbon and therefore would tend to pull electrons away from the carbon, forming polar covalent bonds. Therefore, we can assign a hypothetical oxidation number to the oxygens of 2 minus, and as a result, then this would require that the carbon have a charge as well. So, in this particular compound, if we were to say that there are 2 oxygens, both being 2 minus, then the carbon would have to be 4 plus. This slide does this process of determining the oxidation number in a little more detail. So if we wanted to know the oxidation number of carbon in CO2, we can follow our rules to determine what is the oxidation number for the atom of interest. The molecule itself has an overall charge of 0. The charges of the individual atoms have to be added together to come up with the overall charge. So in this particular case, we can say that the oxidation number of carbon is given the variable X subscript C, whereas the oxidation number of the oxygen is given the symbol of X subscript O. And so there's only one carbon atom times whatever its oxidation number is. There are 2 of the oxygens with times whatever its oxidation number is, and that's got to equal 0. In this case, then, we know that the oxygen, 99% of the time, the oxygen oxidation number is -2. We put that in for x0. We now have an equation with one variable, and we should be able to solve that. So we can see that 2 times 2 minus is -4, and the value of x of c has to be equal to +4. As another example, if we want to determine the oxidation number of an atom in a polyatomic ion, we have to recognize that the sum of all the oxidation numbers for the atoms involved have to add up to the charge of this ion. And so an example of this might be what is the oxidation number of manganese in the so-called permanganate ion, MnO4, with a -1 charge. So we have 2 elements. Again, we have our general formula. So in this particular case, the X of the manganese is what we're going to try to figure out. There's only one of those atoms. But we have 4 oxygens, 4 times the oxidation number of the oxygen, and that's got to equal -1. In this case, we follow the rule that oxygen is typically -2 for an oxidation number, and so now in this case 4 times -2 is -8, and if we then recognize that that has to add up to being -1, the manganese must be a situation where it is +7. As a final example, we have an ionic compound where we need to take into account both the cation and a polyatomic anion. And so we have three elements where we need to determine the oxidation numbers: potassium, chromium, and oxygen in potassium dichromate. So in this particular case, there are 2 times the oxidation number of the potassium, and then 2 times the oxidation number of chromium, and 7 times the oxidation number of the oxygen, and that has to equal 0. In this particular case, then, the oxygen is most likely -2, as we've been done all along here. But also then we have a situation where the potassium is more than likely a +1, so 2 times the +1. And then that leaves us with only one variable to solve for in this equation. We can simplify this down to 2 plus the x of the chromium, and that's equal to -2 plus 14. We do further simplification, and we see that the right-hand side is +12. We then can take and divide the 12 by 2 to come up with the oxidation number of the chromium, which has to be 6+.